Hello, this is Professor Dan Kernler again. This is part of my Calc 3 video series. In this one we're doing section 15.7. We're talking about maximum and minimum problems. And in this first video, we're going to do 3 for this section. In this first video, we're going to talk about critical points and what those are, what those look like in 3 dimensions. So first of all, let's take everything back to Calc 1. You remember relative maximums. Whoops. Get my pen back here. A relative maximum, relative minimum. Maybe you have a relative minimum that's a cusp. And so you have a couple of things you can do there. First of all, to identify them, for the first couple, the derivative would be 0 at those specific values. For the second one, the derivative would not exist. And you might recall there were 2 different tests to identify whether it was a maximum or a minimum. The first was the first derivative test. You make a little chart. You put your value, you have f prime. For a maximum, it would be increasing and then decreasing. So it'd be the first derivative would be positive, then negative. For the relative minimum, you make your first derivative chart. It would be negative before, so decreasing and then, and then positive. Oh, I erased too much there. Positive. And so that would make it a relative minimum. Same thing for that second relative minimum. That's the first derivative test. And then there was the second derivative test. The second derivative tells us concavity, right? The curve, the shape of the curve. And so for a relative maximum, that's concave down, so the second derivative there would be negative. And for a minimum, the second derivative would be positive. So now our question is, how does this extend to multivariable functions? Specifically, we're going to focus on functions of 2 variables, and so our third variable, the z, is like thinking of this in 3 dimensions. First thing we're going to do is give a mathematical definition for relative maximum and relative minimum. So a relative minimum would be, right, we have some kind of like parachute thing here. We have this relative minimum down here at the bottom. So a relative minimum means all of the function values are at least as big as the function value at that minimum for all xy in an open disk. So what this means is if you look in your xy plane, say here's your point x naught, y naught, all of the z values for all of the points around there have to be above that. So there has to be some open disk around here so that all of the z values, and there of course we can't really draw them, they're above that. All of the z values in that open circle are above the z value at that initial point, in the middle point. For the relative maximum, same idea, right? We have some kind of, it's hard to draw these in 3 dimensions, but here we have our relative maximum. And so for there, all of the z values around that point have to be below the z value at that point. So that's what our definition of relative minimum and relative maximum. All right, so now the theorem about how to find them. The key here is that if f has relative extremum at a particular point, then either, notice how the partial derivative with respect to x equals the partial derivative with respect to y, and they are both equal to 0. So that's an and. Both partial derivatives are 0, or at least one of them doesn't exist. So that's similar to what it is in functions of 1 variable. And in this case, we call these critical points. And here, like you might have used that term in Calc 1, but now here in Calc 2, that's actually applicable. They are points in the xy plane where the derivative does not equal, or the derivative doesn't exist, or both partial derivatives are 0. Okay, so let's look at an example here. We're going to find all critical points of this function. So to find the critical points, we're just going to set the partial derivatives equal to 0. Let's take the partial derivative with respect to x. That'll be, let's see, 2 times x minus 2, and then everything else is 0. Similarly, for the partial derivative with respect to y, I feel like I need to align my pen here. That will be, let's see, that'll be 2/4, so 1/2. Times y minus 4, everything else is 0. We're going to set both of those equal to 0. We need the partial derivative with respect to x equal to 0, and we also need the partial derivative with respect to y equal to 0. So that means we need x equal to 2, and we need y equal to 4. So that means our critical point is the point 2, 4. That's a pretty simple one. They won't all be that simple. Let's look at another one, a little more complex derivative, but not necessarily a more complex solution. So we're going to find all critical points of this function. This is a hemisphere shifted down 2. And let's take a look here. We need to find the derivative. Let's write g of x here as 16 minus, I'm going to put a bracket there, x minus 1 squared minus y plus 3 squared, all of that to the 1/2 minus 2. And we'll then do the chain rule. So the partial derivative with respect to x will be 1/2 times 16 minus x minus 1 squared minus y plus 3 squared to the negative 1/2, and then chain rule multiplying by the derivative of the inside, but we're differentiating with respect to x only. That will be negative 2 times x minus 1. And if we simplify that, the 1/2 and the negative 2 simplify, we're just left with negative x minus 1 over the square root of 16 minus x minus 1 squared minus y plus 3 squared. I think I am off the screen here. I think I am off. Shift that over a little bit. Sorry about that. I got to remember not to write over that far. And then similarly, the derivative with respect to y is going to be the same idea. I'll let you try that on your own. That is negative y plus 3 over the square root of 16 minus x minus 1 squared minus y plus 3 squared. Okay, we want to set both of those equal to 0. The partial derivative with respect to x equals 0 means x is equal to 1. And we also want the partial derivative with respect to y equal to 0. It means y equals negative 3. And so again, the critical point, we need both of those to be true. So the only way they're both true is at the point 1, negative 3. All right, scrolling down, I'm going to shift back over. Got to remember not to write so far to the right. Find all critical points of this function. So same idea, derivative with respect to x. Let's see, this is even, I feel like we're getting simpler here. Oops, this is not an f, this is an h. 1/2 y, we want those both equal to 0, and so we just get x is equal to 0, y is equal to 0, and so we have the critical point 0, 0. So now one question that often comes up here is what happens if we solve those and we still have x's and y's available? So we're going to talk about that next in the next video, about what happens when we do that. And then there's going to be an example that we'll see where that will come up. But this is going to be the end of this video. In our next video, we're going to talk about how do we determine whether a critical point is a relative maximum or relative minimum.